Okay.
Good evening, everybody. Welcome to the Santa Barbara Astronomical Unit's public meeting for Friday, the 1st of July. We have a wonderful speaker tonight who our Vice President will introduce very soon. But before that, we have a special announcement from the Santa Barbara Museum of Natural History's representative, KrissieC.
Thanks, Jerry. I would like to issue a special invitation to members of the Santa Barbara Astronomical Unit, calling all SBAU members. As you may or may not be aware, probably you already know that the James Webb Space Telescope will be releasing its very first astronomical image on July 12th. And the museum has been selected as one of the first image host sites. So that day, the museum will have special access to a live expert panel, a NASA-led expert panel, all about that first image and what's in it and why people are excited about it and what we're going to do with all the data. This is not available to the public. You cannot stream it somewhere else. If you would like to participate, you are all invited, AU members, to Farrand Hall. You'll need to be live in person at the museum at 3 p.m. on Tuesday, July 12th. Again, that's Tuesday, July 12th at 3 p.m. in Farrand Hall. And we will be streaming this live webcast from NASA all about that first image. We here at the museum, we love you, AU, and we want you to come. And we're not inviting the public to this. We're inviting museum docents, astronomy volunteers, and the AU. And that's it. You're on a special short list.
Okay.
I'd love to see you there.
Thank you very much. I'll see you there.
Chrissy, does that supersede that 10 a.m. video that we talked about?
It does not.
Okay.
No.
That's still happening.
All
Okay.
right, cool.
Was that an early version for the select of the select?
No, that's a special video the museum was going to put together and release on social media that will
Oh, okay.
feature some of us.
Yeah.
Hey, Tom.
Folks, I don't seem to see the YouTube coming out live, so I'm thinking about restarting the live on YouTube.
Oh, I'm seeing it live on my screen. I've got
Yeah,
it.
we are too.
Okay,
Yeah.
so I'm not just not on my show. Okay,
No, it says it's on for me too.
so you got a show.
Well, we'll have next up will be Chuck with an announcement of our outreaches.
Okay, lots of outreach, mostly campgrounds this month. Saturday the 2nd, tomorrow is Cachuma Lake, starting around 8, probably 8:30 before it's dark enough for the slides to come up. But we'll have telescopes out in Dakota Plains, and we'll have slideshow down in the Fireside Theater. Then Tuesday the 5th is Telescope Tuesday, set up at 7 o'clock at Camino Real Marketplace, because we're looking at the moon mainly with all the lights there. Although Tom came up with some great shades for the new lights they put in.
Yay.
And then on Friday the 8th is Refugio State Beach, again starting around 8. On the 9th, second Saturday, that's the Museum of Natural History Public Star Party, and we'll meet before that at 6:30 for the planning meeting. And then the actual star party goes from 8:30 to 10. And then, of course, on the 12th is that James Webb Space Telescope event Chrissy just mentioned. On the 14th, Refugio again, starting around 8, and we set up in the southwest corner of the JWST parking lot. Third Friday, the 15th, Westmont Public Telescope Night. Again, come when it's dark. They officially announced it as happening at 7 o'clock, but I guess we'll have the moon to look at, but people show up because of that. And also their phone number, which was disabled for quite a long time because it always said the observation is on. There is a phone number you can call that's in our announcements that you can call ahead of time if you're from far away and check on the weather and see if we've canceled it or not. And then on the 16th is Carpinteria State Beach, again with a slideshow on telescopes. Refugio again on the 22nd, Friday the 22nd. 23rd, Saturday, Cachuma Lake again. And then on the 29th and 30th, same thing. Friday night at Refugio, Saturday night at Carpinteria State Beach. So we're basically got every Friday and Saturday until October booked with campgrounds or the museum or Westmont. So that's it for outreach.
Okay. And now we'll go to our vice president.
You don't want to, Jerry, would you like to announce real quickly next month, August? We're going to meet live, right?
Will be verified. That's our operating plan right now is to meet on what is it, August 5th?
Right, Friday the 5th.
The first Friday of the month, to meet in Farrand Hall. A number of us will be there. The speaker will not be there. The speaker will be piped in via Zoom. And the meeting can be watched for those that don't want to come to in person. The meeting can be watched on Zoom, on the Zoom link, the same link we're on right now. But that's the operating plan. The final decision will be made a week from tomorrow at our business meeting to go ahead or not, depending on COVID.
It may not be the same link because it's going to be a webinar.
Okay, that's right. That's right.
That's right. Okay. Well, am I introduced? My name's Baron Ron Heron. I knew these guys on the radio twice a month on Mondays, and we decided after I left the radio industry to go once a week on Zoom. We're having a lot of fun, and we'll have a program number 71 to broadcast live on Monday morning coming up in 4 days. This month, boys and girls, we got NASA. JPL was very forthcoming in providing us with a qualified veteran science speaker. And I'd like to tell you about him real quick. Exoplanet astronomer and expert at NASA's Jet Propulsion Laboratory, working on ground and space-based observations of the atmospheres of distant worlds orbiting other stars other than our sun. Rob is a member of the Nancy Grace Roman Space Telescope, which the coronagraph instrument, CGI, I'll let him tell us about that, an instrument that directly images exoplanets. And I assume they're looking for life on them. They can figure it out. He's the lead in developing the science calibration plan. He's going to have to explain that too, as well as the JPL commissioning lead of Nessi, Nessi, at Palomar Observatory. Without further ado, ladies and gentlemen, let me introduce you to Dr. Robert Zellem of JPL.
Hi, everyone. Thank you so much for having me. Really appreciate it. And I was actually in Santa Barbara last week at a conference, so I'm missing the funk zone like mega right now and having all those delicious breweries. So thanks for that awesome intro. Thank you again for having me tonight. So I'm Rob. I study exoplanets and the ultimate goal of finding life in the galaxy. And I'm a giant nerd. So if I go too quickly or if I say things that you're not following or I haven't explained too well, please feel free to interrupt. And I do have the chat up on my screen as well. So you can also send me messages via the chat. So I work at NASA's Jet Propulsion Laboratory. That's out here in Los Angeles. I live in Monrovia, just a few miles east of there. This is a picture of JPL in the San Gabriel Valley-ish, obviously taken thousands of years ago when LA had water back in the day. My building's here. I actually got a question prior to starting this about how often I go on the lab. Right now, I'm going on the lab about twice a week. And the other 3 days a week, I'm telecommuting. So got to save some gas money, which is always very nice. So at NASA's JPL, I study exoplanets, planets outside of our own solar system, and I've always been interested in space. Here I am, little Rob, about 6 or 8 years old, at Kennedy Space Center, my hero, the astronaut. And lots of people ask me if I ever wanted to be an astronaut, and the answer is a hard no, because I'm deathly afraid of heights. So I'm what I think is the next best thing. I'm an exoplanet astronomer. So let's unpack this a little bit. An exoplanet, that's just short for extrasolar planet, where extrasolar means anything beyond or outside of our own solar system. Planet, hopefully you all know what that means. Otherwise, you might be in the wrong club. So an exoplanet is any planet outside of our own solar system. And then astronomer, you all probably know what that is. That's someone that stares at the sky, or more likely, definitely in my case, their computer for way too long. I actually spend most of my time working on my laptop, whether here in my home office / guest room or on lab. And I only get up to the telescope maybe about 8 to 10 times a year. But in between that, I'm working on missions, on instrumentation, on a citizen science project I'll be talking about tonight. But as an exoplanet astronomer, what I'm doing at JPL is characterizing exoplanets, trying to figure out their composition, what's in their atmosphere, if there's water, methane, carbon dioxide, if these planets could be habitable, if they have the right conditions for life. And if they are habitable, maybe they could be inhabited, actually have life on them. And that's the ultimate question I'm working towards, is helping ask or answer this question, are we all alone? So before we look to where we currently are in astronomy and exoplanets, and we're looking towards the near future, it's always helpful to look back into the past. Also, my wife is a historian, so I'm legally obligated to show this slide to you, so just 1 second. The study of exoplanets is actually one of the newest fields in astronomy. It's been around since roughly the mid-90s when the first exoplanet was ever discovered. But the idea of exoplanets, about planets outside of our own solar system, is nothing new. Giordano Bruno, that's the Emperor Palpatine looking like guy in the top right, he was a 16th century philosopher who postulated the idea of planets being outside of our own solar system. And Isaac Newton, you all know him, he's the guy that discovered fig Newtons. He actually wrote in his book Principia, when he actually discussed his theory of gravity, he said, and if the fixed stars are the centers of similar systems, they will all be constructed to a similar design. In other words, when we go out into the night sky and look up at all the stars, it stands to reason that there might be planets around those stars as well. Just like there's 8 planets, 8 because Pluto's not a planet, 8 planets around our own sun. Perhaps there's also planets orbiting around those stars. And we now know, hundreds of years later, that these 2 dead guys are absolutely correct. We've actually discovered over 5,000 now, this slide's a little out of date, over 5,000 exoplanets. And as we figured out how to look, where to look, when to look for these planets, we have been discovering them more and more, and their discovery rate has gone up exponentially. As our technology gets better, as we know where to look and how to apply the techniques to discover exoplanets, we are finding that exoplanets are everywhere. On the whole, there are at least as many exoplanets as there are stars in the sky. And perhaps where there are planets, there could also be life. So how do we find life? Well, let's just break it down in this 3-step method. First, you have to find an exoplanet. Then you have to determine if that exoplanet could support life. Then you have to find life. So you have to find the planet, you have to determine if it could support life. Just because it could doesn't mean it does necessarily. And then you actually have to find the life on its surface. So let's look a little bit in more detail about the various methods on how we find exoplanets. Well, this is actually a big problem because it's very difficult to see them. They're so far away, we only typically see the light from the star that it's orbiting because the star is so much brighter than the planet itself. So we either need to block out the light from the host star or use other methods to indirectly infer that that planet is there. And there's actually many different ways to find exoplanets. But the 3 I'll be focusing on tonight are the radial velocity, the transit, and the direct imaging methods. The radial velocity and transit methods have arguably given us the most information that we know to date about exoplanets. And the direct imaging method I'm sort of required to talk about because I work on a mission that uses direct imaging and I don't want my bosses to get angry. So let's first look into the radial velocity method. This is sometimes called the Doppler shift or the wobble method. When you have a planet orbiting around a star, the star's gravitational pull will cause the planet to orbit around it. But the planet itself is also gravitationally tugging on its host star. So when the planet orbits around the star, it causes the star to wobble back and forth. And as the star comes towards us, the star's light, its wavelengths are effectively shortened, and that increases the frequency or pitch. So it's like when a car passes you or an ambulance passes you on the side of the street, you can hear that increase in pitch of the sound waves as it gets closer towards you. That's the sound waves being basically compressed. And then as the ambulance goes away from you, those sound waves are then pulled apart and the frequency dips. And the same exact thing happens to light. As the star wobbles towards us, its light is blue shifted. And as the star recedes from us, its light is red shifted. Now, this only gives us the motion along our own line of sight. If I see a star moving this way, I will not see a radial velocity at all. And I won't see that Doppler shift. I won't know that a planet is there. But this method is extremely crucial because this gives us the planet's mass. The bigger the planet, the more it gravitationally tugs on its star, and the faster that star or the larger that star wobbles to and fro. So this actually, very importantly, allows us to effectively weigh exoplanets. Another method that's really near and dear to my heart, because this is where I specialized in my PhD, is the transit method. And the transit method, what it does is it measures the change in brightness as a planet passes in front of it. So let's say, pretend that we're looking at a star, and if we're really lucky, a planet will pass in front of that star. And the planet will block out some of the star's light and cause the star to appear to dim. Effectively, the planet's actually casting a shadow all the way on the Earth. And the bigger the planet, the more light it blocks out. So this effectively gives us the planet to star radius ratio. This tells us how big that planet is relative to its host star. This method is also extremely helpful because it allows us to study the planet's atmosphere. When the planet passes in front of a star, not only does the optically thick or the very dense layer of the planets block out star's light, but also the atmosphere of the planet absorbs some of the star's light as well. And we can use that information, as I'll describe a little bit later, to actually study the planetary atmospheres and to actually look into their composition. And the transit method has been used very, very successfully, thanks mostly due to ground-based surveys and also space-based missions like NASA's Kepler and TESS to discover over 3,000 of the currently known, actually 5,000 currently known exoplanets to date. So we know a lot of information both from the radial velocity and the transit methods. One advantage of the transit method is it's actually relatively cheap to do. I saw someone who posted online for a few years ago, they put a DSLR camera and a simple barn door tracker, and they're actually able to observe an exoplanet. We're finding that in our citizen science project, people with telescopes as small as 4 inches can actually provide scientifically valuable and impactful observations of transiting exoplanets. I'll talk about that a little bit more later. And again, the transit method is crucial because it gives us the planet's size. The bigger the planet, the more light it blocks out, the bigger the dip in the brightness of the host star. But there's some disadvantages. You're biased towards large planets in short period orbits. Bigger the planet, the bigger the signal, the easier it is to see. You can have false detections. And also you need that geometry. The planet's orbit must be seen edge on from the observer's point of view, much like the radial velocity method. So if I have a planet orbiting perpendicular to my line of sight, I won't see a transit and I won't know a planet's there. But one NASA mission that's using the transit method very effectively is NASA's TESS mission. This is the Transiting Exoplanet Survey Satellite. This is an all-sky survey that's looking for and discovering new exoplanets. Here's an image of TESS right here with its solar panels, its high-gain antenna. And right here are 4 cameras that are positioned and basically looking at a slice of the sky. And over a calendar year, it'll slew around the entire northern and then southern hemispheres and discover exoplanets. TESS has discovered a few hundred, I believe, to date, and TESS is predicted to discover an additional 10,000 exoplanets. So today we know 5,000. TESS will triple that number with an additional 10,000 new exoplanets, hopefully. So you might be wondering, if we already have 5,000 in the books, what's the purpose of needing to discover another 10,000? And that's because we want to find the ideal targets to observe and follow up with to characterize their atmospheres with large ground-based telescopes and also space-based telescopes. The Hubble Space Telescope, for example, has already looked at tens of planets, about 50 or so. James Webb, which just launched a few months ago and is actually slated, as you told in the intro, to do its first science observations within this month now, actually. We'll be looking at tens to hundreds of planets. Ariel, it's a European Space Agency mission. This will be looking at hundreds to 1,000 exoplanets. This is a mission built by the Europeans that will be launching roughly around by the end of this decade that is dedicated to observing and characterizing thousands of exoplanets. And then looking beyond that, next generation missions and future missions will likely continue to use the transit method to characterize the atmospheres of exoplanets. But if I want to observe a transit, to characterize the atmosphere of an exoplanet, I have to know very precisely when that transit occurs. So let's pretend I'm writing a telescope proposal for like James Webb or Hubble. And I write my proposal and I look up transit timing information or predictions of when a transit will occur. And I see online that it's predicted, for example, to have a transit here. But there could be some uncertainty in that timing. The transit could come a little bit earlier or a little bit later than I anticipate, simply due to measurement uncertainties in the data. So I can do one of two things. One, I can widen my observing request to ensure that I observe a transit event. However, at the end of the day, that's not really using large telescopes really effectively or efficiently. James Webb and Hubble are really precious resources, and everyone in astronomy wants to get on them. So you really want to use these resources as efficiently as possible. Or what you can do is you can actually take some pre-imaging from, for example, ground-based telescopes, and you can measure a transit event maybe a few days or a few weeks before your planned observations and update the timing. And that's exactly what we started thinking about. Was we realized this problem with needing to know these really accurate times. And at the same time, we were working with some data from a 6-inch observatory called the Micro Observatory, operated by Harvard CFA in Tucson, Arizona. And we were honestly blown away by the data quality. The Micro Observatory is a collection of 6-inch telescopes both in Tucson and Cambridge, Massachusetts. And those are robotic telescopes. They're not even perfect guiding. They're not even optimized for exposure times. All their exposures are 60 seconds. There's actually some sample data we took from the Micro Observatory of an exoplanet called HAP-P32b. And on this exoplanet that they're observing, it's actually relatively dim host star. It's dimmer than 11th magnitude. It's a relatively small signal. And the tracking on the Micro Observatory is imperfect. The target's slewed by over 300 to 500 pixels. The exposure time wasn't ideal, and also there's no calibrations taken. So no flats, no darks, and no biases. Despite all of those sort of issues, we're able to get a really nice looking transit light curve. We're observing the host star, the planet passes in front of the star, blocks out the star's light, and then the planet gets back out of the way, you observe the unocculted star. And we're getting really amazing measurements. And we realized really quickly we can actually make science-grade observations with this data. So this inspired us to launch a project called Exoplanet Watch, where we're inviting citizen scientists to monitor transiting exoplanets. Exoplanet Watch is a campaign aimed at citizen scientists to routinely observe these high-priority transiting exoplanets. We have hundreds of people across the world, and they have telescopes as small as 4 inches, some as large as half-meter to a meter class telescopes. And we have people in dark sky conditions and also very light polluted areas as well. And we're finding that you need a very modest sized telescope, again, 4 inches, and you can also tolerate light pollution. You have someone just down the road from me here in LA that's making routinely scientific grade light curves and measurements, despite them having to deal with the light pollution nearby of LA. So our project is a collaborative effort to complement existing surveys. We have an open collaboration with EXOCLOCK, which is sort of the European version of Exoplanet Watch. We're also a member of TFOP, the Test Follow-Up Program, and also a member of LCO, the Las Cumbres Observatory. All of our data will be immediately public to the entire community. Right now, we're releasing data products every 2 days. There's no proprietary phase. There's nothing hidden. Everything is on our website, immediately available for anyone to go out and grab. There's also an opportunity for community feedback. So professional astronomers, for example, if they have an upcoming run on a telescope, they can contact us and ask us and our users to help monitor their target. And we've actually done that a few times last year, and we're starting a new campaign right now for the Northern Hemisphere. One thing though I'm really proud of though is that we're requiring observers to be listed as co-authors on any published results. So in other words, if you make an observation and your data is included on a paper, we're requesting that that first author includes you on that paper as well. If you do the work, you deserve the credit. And at the end of the day, we're actually funded by NASA's Universal Learning, which is a part of NASA SMD, Science Mission Directorate. So we have two sort of goals with Exoplanet Watch. We have these educational goals, which, engaging the public in exoplanet science, increasing their confidence about their ability to do science, but also we're getting out of all these additional amazing science goals from amateur astronomers and undergraduates and graduate students and high school students, by ensuring that we're going to efficiently use large telescopes by updating the timings of these exoplanets, to discover new ones, to search for blended pairs, monitor for stellar variability, and to confirm new exoplanet candidates as well. So what I'll do right now is I'll quickly just give a quick rundown if you wanted to join our project. Your user experience is that you plan your own observations. We have a nice partnership that recently was established with the Swarthmore Transit Finder, and we actually have our entire target coordinate list on that. So you can look up wherever you are in the world, you can actually look up and predict when an Exoplanet Watch target is going to be transiting locally in your part of the world. You can also use any other tool you want, such as a NASA or Exoplanet Archive planning tool. And while we have recommended targets, you could observe any transiting exoplanet you want. We'll accept data on any target, even a target that's been observed many, many times before, even by the professional community, because there's additional science cases we can actually enable by monitoring this long-term baseline of these targets. Then you make your own observations. So we're launching right now, last summer, we just launched to amateur astronomers, folks that have their own telescopes. But by the end of this calendar year, we'll be launching it to the general public. And we're actually working on getting data from some robotic telescopes to give out to folks by the end of this calendar year. So if you don't have your own telescope or you don't have access to a robotic telescope, you can actually contact us and we can actually give you data that we've taken either from one of our partner observatories, such as Las Cumbres Observatory or the Micro Observatory, or one of our telescopes out here at JPL. We're actually getting ramped up to start observing on a 0.4 and a 0.6 meter telescope starting in August. And we'll hopefully have hundreds of observations by the end of the calendar year. I'll be getting out to people. Then you analyze your own data. So what you do is you actually take your raw FITS files and you fully analyze and reduce them. And you can use whatever analysis software that you want. We have our own in-house software called Exotic, I'll be talking about in a few minutes. Tons of people love AstroImageJ and use that all the time for exoplanet data analysis, or you can use your own homegrown data software. It doesn't really matter. All that matters at the end of the day is that your data is in the correct format to send off and contribute to the AAVSO. We're very lucky that we have this partnership with the American Association of Variable Star Observers. They're actually letting us use their exoplanet database for free. And all of our users' observations are uploaded directly to the AAVSO exoplanet database. And as long as your data is in their format, that's all that matters at the end of the day. Then you sort of sit back, relax, open a bottle of beer or something, or pour yourself a glass of wine, and then you just get published. So this is actually a screenshot of one of our papers we published back in 2020. And about half of the co-authors on this paper are citizen scientists, high school retirees. We run the gamut of all the years as well. And we're very, very proud that we're helping enable, hopefully, more folks getting involved and contributing directly to NASA science. And then what's happening on the back end is our pipeline called CITISENS. This is actually not a misspelling. It's an acronym that stands for Citizen Initiated Transit Information Survey Enabling NASA Science. It's a mouthful, but it's a fun pun. So there we go. The Citizens pipeline is basically two servers out here at JPL. And what they do is about every other night is they reach out, they scrape or download all the data on the AAVSO's exoplanet database. We then reprocess the data or refit it with a new transit model. And the reason we do this is in case some values get updated by subsequent surveys. And then again, we immediately publish all of our results to our website. And actually this figure that I made a few days ago is already out of date. We have over 200 targets right now. We have over 810 or 20 total reductions, and we saved about 2.5 hours. So if a mission like Hubble or James Webb were to observe these targets, we would have saved them 2.5 hours. So you might be thinking 2.5 hours is not a lot of time, But if you do the math, 1 hour on James Webb is about $1 million. So that's $2.5 million we're potentially saving there. So if NASA could write me a personal check, that would be awesome. So I mentioned a little bit earlier, Exotic. This is our own data analysis tool. And this is basically your one-stop shop for analyzing and reducing all of your data. It takes your raw FITS files. It can apply flats, darks, and biases and other flats as well. And then it performs multi-object photometry on your data. It picks the optimal aperture size, the optimal sky annual size, as well as the best comparison star in your data. And then it fits that data, which is unique, to an actual science grade light curve. So the plot that I was showing earlier before is actually, that microobservatory data set was actually analyzed by Exotic and was included in our paper that we published in 2020. And it runs in only about 4 minutes, which is mind-boggling to me, but it also runs on Windows, Macs, PCs, Linux boxes. It also runs on the Google Colab Cloud. And this is really important because if you don't have a nice computer, or you can also actually actively participate in this project by running Exotic on your cell phone or your Chromebook. And as long as you have the data, either from our project, your own telescope, you can actually analyze and reduce it as well. One cool feature that we really like about Exotic is it has this real-time data analysis tool. So when you're observing an exoplanet, they're actually kind of boring observations. You're sitting on a target and staying on it for about 5 to 6 hours. You know, the target, the host star dims about maybe 1%. And when they're boring, that's a good thing. That means nothing is going wrong with your telescope. But, you know, by eye, that's kind of impossible to see that 1%, 3% flux dip. So what we've actually built in is a really quick and dirty analysis tool that quickly analyzes your data and actually builds a light curve in real time. This is really helpful for us when we're like at Palomar Observatory, because this makes sure that we're observing the right target. But also if you're at a star party, you know, you can point at your laptop screen and point to someone and say to someone as they're passing by, hey, look, we're looking at an exoplanet hundreds of light years away. It's passing in front of its star and it's casting its shadow on the Earth. So it's a kind of cool outreach experience you can do to actually show people planets in real time. So if you're interested in joining, again, the bar is extremely low. You only need, you know, maybe a 4-inch telescope and or an alt-az guider, or even an equatorial mount guider, or even a relatively cheap camera. You don't need dark sky conditions. We'd love to have you. And like I said, if you don't have your own telescope or your ability to take robotic data, don't worry, by the end of this calendar year, we'll be launching out and be giving folks access to robotic telescope data so anyone and everyone can participate. So you can find us online at exoplanetwatch@jpl.nasa.gov. You can go to our website there, or I can't ever remember this URL, so I just search NASA Exoplanet Watch on Google, and that usually works for me as well. All right, I'll get off my soapbox. Thanks for bearing with me there for a few minutes, folks. Appreciate it. So next, we'll be talking about the direct imaging method. And as you've probably guessed, the direct imaging method is very aptly named because it's literally taking photographs of exoplanets. However, as I alluded to earlier, there's a big problem in the sense that a planet is so much dimmer than its host star. So let's try to make a little thought experiment here. Let's take a really large planet. Maybe it's relatively young, it just formed a few million years ago. It still has a lot of residual heat from its formation, so it's glowing. Let's take that Jupiter-sized planet, put it around a sun-like star, and let's try to observe it. The problem is that Jupiter-sized planet is 1,000,000 times fainter than its host star. It's like looking for the light of a firefly around a lighthouse and you're on the other side of the country. But, you know, that's all well and good. Hot exojupiters are pretty interesting scientifically, but what we really want to get to is really reach down and sort of get to smaller planets, planets that could have life on their surface, planets that are potentially like Earth. But that Earth-like planet around that same solar-like star is 10 billion times fainter than its sun. That's like looking for one bioluminescent algae around that same lighthouse. So how do we look for these objects? How can we observe these exoplanets when their host star is so much brighter? So some of you probably saw the total solar eclipse that happened a few years ago. And if you remember, when we were observing the sun, the moon passed in front of the sun and blocked out a majority of the solar disk and allowed you to observe the corona and actually see some stars around it. So if we could do something similar, where we take a little moon or a little disk, and if we're able to move that in front of our star, perhaps we can also block out the star's light, much like the moon does of the sun, and allows us to then resolve the dimmer light of that exoplanet. So right here is a quick little video that actually explains all the awesome hardware that goes into doing direct imaging.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk, as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own.
All right, so that's how direct imaging works. Hopefully you all paid attention. There's a quiz after this, but basically it works like magic, right? We have hardware and software that works in unison to block out the light from these stars. And just like with the total solar eclipse where the moon passed in front of the sun, we use on coronagraphs a little disk that moves in front of the star and blocks out the majority of the star's light. Then you use additional hardware, such as that mask, to then further block out the remainder of the star's light. And this is what's being used on the Nancy Grace Roman Space Telescope. I'll be talking about that a little bit later tonight. But this method has been used very successfully on large ground-based telescopes, typically 5 meters or 15 feet or larger, to directly image exoplanets. And here's actually some real data of direct imaging of an exoplanet system. So this was taken, I believe, by the Gemini instrument or telescope. And right here at the center of the screen, you can see this little black disk. That's our coronagraph that we placed in front of the star, blocks out a majority of the star's light. And you can see 4 little pinpoints of light right here. Those are actually extrasolar planets orbiting around its star. And if you look here, this data was taken over about 7 years. So this is an extrasolar solar system where we're actually able to observe the planets orbiting around their star in real time. Absolutely incredible. All right, so now what? So we've discovered over 4,000, actually over 5,000 exoplanets now, and that's all well and good. And planet discovery is kind of passé at this point. Discovering exoplanets is nothing really new. It's almost kind of boring in a sense. I remember when I started off in exoplanets, it was pretty exciting to hear about new planets being discovered all the time. Now it's just kind of like, yeah, okay, cool. All right, we know they're everywhere, not a big deal. So how do we take that next step then from planet detection to discovering planets to then actually characterizing them? Can we, for example, tell if a planet has an atmosphere? And if a planet does have an atmosphere, can we figure out what sort of molecules are present in that atmosphere? Does it have methane, carbon dioxide, carbon monoxide, or water? doesn't have the molecules that are necessary to support life. And just because a planet could support life doesn't guarantee that it does. So then we have to prove whether or not that planet has life on its surface. And that brings us to the next step, actually determining if a planet can support life. So when we think about exoplanets and trying to focus on the ones that could have life on their surface, we use a metric called the habitable zone. So again, today we know of over 5,000, and tests might discover an extra 10,000 exoplanets. And we need some way to go from the thousands of planets we know today to finding or to studying a few in depth and sort of pinpointing our research on the planets that could potentially have life on their surface. And if you look at our own solar system, the only planet that has life on its surface is the Earth. And as far as we can tell, Earth life requires liquid water to survive. So if we find a planet that could have water on its surface, potentially that planet could also have life on its surface. And this is called the habitable zone. This is the zone where liquid water can exist on a planet's surface. The planet isn't too close where it gets too hot and it's boiled away. It's not too far away where that water freezes out. It's in that zone, not too close, not too far away from its host star, where it's just right for water to survive on its surface. So here's a top-down image of our solar system. Here's the sun at the center. Mercury and Venus are a little bit too close to the sun, too hot for water. Mars is a little bit too far away, but the Earth is just right. And as far as we can tell, the only place that has water or life on its surface is the Earth, and the Earth has liquid water. And this is a great metric, again, from whittling down the thousands of exoplanets to the handful that we can then focus on to sort of look for life on its surface. But, we really want to be able to say whether or not a planet has molecules in its atmosphere. And this is something that we actually use a physical law called Beer's law. Beer's law is actually a very, very helpful physical law that allows us to actually peer into the atmospheres of exoplanets. And I was able to, luckily, before this talk, find a really great definition that explains in Beer's law in layman's terms. So that is studying for a test or doing homework while beer is involved, making difficult classes such as physical chemistry more bearable. That's a great one. I definitely did that a ton in graduate school. That's not the right one. Here's the right Beer's law. And what this really describes is the scattering and absorption of light out of a beam. So let's just do a thought experiment. Let's say we look at a light bulb and we put it on the other side of a chamber of gas, and maybe let's put carbon dioxide gas in that chamber. So we have the light bulb on one side, we have our chamber of gas. Then we look at the light bulb on the other side, we'd expect that light to look a little bit dimmer. And that's because the chamber of gas of carbon dioxide is absorbing some of the light from our light bulb. And the way that it actually absorbs or scatters that light adheres to this relatively simple equation here, which is Beer's law. So in other words, what we can actually do is if we compare what the light should look like, not absorbed, not scattered by that chamber of gas, and compare it to what it does look like, the light looks a little bit dimmer at certain wavelengths, we can actually use Beer's law to actually back out the makeup of what's in the chamber of gas. We can actually look at light and figure out that that chamber of gas is full of carbon dioxide. Well, let's take this analogy a little bit farther. Let's say we're observing through our telescope a yellow star. We expect that star to look yellow, right? But what happens if we place a cloud of gas and dust between us and that yellow star? Well, what happens is that cloud of gas and dust absorbs some of the yellow star's light and causes it to appear a little bit more red. And if we can observe what the object does look like, red, the star looks a little bit more red, and compare it to what it should look like, it should be a yellow-looking star, we can actually use Beer's law to determine the composition of the absorber. And we can actually figure out that that cloud of gas and dust actually has molecules in it. We can also apply this to exoplanets. So let's say we're observing an exoplanet, and just like the Earth, a lot of these planets have really hot cores that radiate heat and light. And on some of these planets, they're like Jupiter-sized planets. They have very, very thick atmospheres. And the outer layers of the planet, since they're farther away from the core, are a little bit cooler. So as that hot yellow light radiates away from the center of the planet, it goes through layers of the atmosphere of the planet that are a little bit cooler. So the yellow light actually comes out red when it's finally emitted from that planet. And we can use Beer's law. Astronomers on the other side of the telescope can figure out that that planet has methane in its atmosphere. We can also apply this for reflections, for example. In our own solar system, we have Jupiter. And when the sun's yellow light hits Jupiter's surface, it reflects back a little bit red. And astronomers on the other side of those telescopes can say, hey, there's clouds in the atmosphere of that planet. So Beer's law is absolutely crucial in the sense that allows us to characterize an exoplanet's composition by observing how it emits, absorbs, and reflects light. So purely by using light alone, we can actually figure out what exoplanets are made out of, which is really handy because they're super far away, right? The nearest exoplanet is about 3 light years from us, thousands upon thousands of years to travel to, which is not a great way to write a PhD thesis. So here's some actual data of exoplanets. This has taken the light from these planets and put them through a prism. So if you've ever seen the Pink Floyd's Dark Side of the Moon, you have that white light going into the prism, that little triangle piece of glass, and the rainbow coming out. This is taking those exoplanets' light and sort of spreading them out over various wavelengths. On this axis, we actually have data from about 7 exoplanets. And on this axis, we've ranged them from cool to relatively hot at the top. And this axis is the wavelength of light. And at these wavelengths, water absorption dominates the spectra of exoplanets, the signature of these exoplanets. So if I see a bump and wiggle at these wavelengths, I can infer that that planet has water in its atmosphere. And again, this data is spectroscopy, actually, I think from a ground-based telescope, Gemini. So we're actually able to potentially start looking for water in these exoplanet atmospheres. At these wavelengths, this is where methane absorbs light most strongly. So if you see a bump and wiggle at these wavelengths, you can infer that planet has methane. And then at this atmosphere is where carbon monoxide absorbs light most strongly. So some of you eagle-eyed observers out there probably noticed these sort of breaks in the data. Again, I mentioned that this was data from the Gemini telescope here on the ground. And this is actually where the Earth's atmosphere gets in the way. The Earth, unfortunately, has lots of annoying molecules in its atmosphere, like water, like oxygen, things that get in the way from us observing exoplanets. It's kind of like looking through a picket fence, right? The Earth's own atmosphere is that picket fence that gets us in the way of observing molecules through the planet's atmosphere. So actually certain wavelengths are inaccessible to us from the ground. So if you can't observe it from the ground, what do? You go up into space. And this is why space-based observatories are so very important. They allow us to go above the Earth's atmosphere to basically look over that picket fence and allow us access to many wavelengths that we do not have really access to on the ground. This is what we've been doing for the past decade or two with the Hubble Space Telescope, and has observed about 50 exoplanets using spectroscopy to characterize their atmospheric composition. And this is why we're so very, very excited about James Webb, which again, will start doing exoplanet observations this month. It'll be doing spectroscopy to characterize the atmospheres of over up to 200 exoplanets or so. And James Webb, comparison to Hubble, Hubble was a 2.4 meter telescope. James Webb is about an 8.5 meter telescope, or about, let's see if I can do math in my head, 24 or so feet across. That's the yellow primary mirror here, about 24 feet across. It's an absolutely massive telescope. This is its purple sun shield. That's the size of a tennis court. It was so massive that they actually had to fold it in on itself like origami to fit inside of its rocket nose cone fairing. And then it had to unfurl itself, which it's been doing over the last few months. And now it's about to do observations of exoplanets. We're really excited about using James Webb because not only is it larger than Hubble, so it has higher precision, the data has lower scatter, lower uncertainties, but also James Webb allows us to study many more wavelengths of light than Hubble does. So we're actually able to observe many different molecules, much more molecules than Hubble can. So you can actually start looking into a complete budget of the atmospheric content of these planets. So I see I got a question online if it's easier to detect exoplanets and their atmospheres around red dwarf stars. That's an excellent question. So for everyone who else is on the line, a red dwarf star is a very small star compared to our own sun. Typically, a red dwarf is 10 times smaller than our own sun, and they're a lot cooler than our own sun as well. And it's easier to detect an exoplanet around a red dwarf versus a G dwarf like our own sun, because the planet is, since the star is so much smaller, that's a lot more light that the planet will block out as it orbits around its star. So the signal of a transiting exoplanet will be larger. And that's why TESS, actually, this mission that's discovering new exoplanets, is mostly focusing on nearby M-dwarf stars to find targets that can then be easily followed up and observed by the James Webb Space Telescope. Thanks for that question. So James Webb will be doing the transit method, the direct imaging method, but looking beyond James Webb to the next generation missions is the Nancy Grace Roman Space Telescope. This is formerly what was called WFIRST. This is a space telescope that is named after Nancy Grace Roman. She was the first chief astronomer of NASA, and she's sometimes referred to as the mother of Hubble because she was one of the chief proponents of actually space-based observatories. So in her honor, they've named this telescope after her. This is a Hubble-sized telescope, so about 2.4 meters across, and it'll have 100 times the field of view of Hubble. But one thing that I'm really excited to be working on is direct imaging of exoplanets. This will be applying the same techniques and technology that we've been using on large ground-based telescopes for the first time on space-based observatories. So right now, with current technology, we're limited to looking at big planets that are big and bright. They still have residual heat. They're still glowing in the night sky, very, very far away from their host star. What Roman and its instrument, the coronagraph instrument, or CGI, of which I work on, this is basically a technology demonstration. It'll be taking this technology that works so effectively on the ground and demonstrating it for the first time in space. And what it will enable us to do is to look for planets that are a little bit cooler and closer to its host star. And you might say, okay, Rob, what's so important about observing Jupiter-like planets, around roughly Jupiter temperature planets as well? And it's because Roman CGI gets us from where we are to where we want to be. We want to be able to observe with future missions, small Earth-like planets close into their host stars. We want to be able to observe exo-Earths and use Beer's law to characterize their atmospheres to look for signs of life on these planetary surfaces. So one thing that these next generation missions will be doing that learn from Roman CGI is they'll be adopting all the technology and the lessons learned from Roman CGI and applying it to those next generation missions they'll be launching in the 2030s. And these next large flagship missions that NASA will be launching, 2030s, 2040s, we'll be looking for signs of life, for things such as oxygen, and looking for other things like water, carbon dioxide in these exoplanet atmospheres to then look for life. So hopefully I've sold you on space-based observing. I'm on the Roman project science team. I'm the science calibration lead. So basically what I do is I spend most of my day trying to figure out how to calibrate Roman CGI as effectively as possible to remove as many sources of noise out from our data as possible. Again, we're looking for a signal that is 1 times 10 to the minus 9 smaller than our host star. So 1 billion times smaller than our star signal. And to look for such extremely small signals, we have to remove as many sources of error and other things like doing flat fields, for example, or darks or biases. Those images can help remove sources of noise and allow us to see that really small signal even better. So you might be wondering though, Rob, you sold me on space-based observatories. I love it. I want to give you all my tax money to get more space-based observatories. That'd be great. Why even bother with the ground? Well, space-based observatories are awesome. You're not limited by Earth absorption. You're minimally impacted by sunlight. However, you're very, very limited in the amount of time in wavelength space. Right now, there's really only 2 telescopes that can do transiting exoplanet spectroscopy, HUBBLE and James Webb. And both of these observatories are being routinely applied to by the rest of astronomy as well. Everyone wants to get on these two telescopes due to their capability, their wavelength range, their sensitivity. And it's very, very competitive to get on these telescopes. Also, let's say you discover that instead of looking at these wavelengths here, we should be looking at this new wavelength out here. It's very, very difficult to send something up, a mission, to add on new instrumentation. But on the flip side, ground-based telescopes, you just have to get in your car and drive out to there. And you just slap your instrument on the back. There's also numerous platforms and instrument combinations on ground-based telescopes. But you have to deal with annoying things like the Earth's atmosphere, the sun, weather, all that stuff I'm sure all of you are fully aware of. But keeping that in mind, this is why we're commissioning a new instrument at Palomar Observatory. Here's the 200-inch Hale telescope at Palomar Observatory, where Nessi, our New Mexico Exoplanet Spectroscopic Survey Instrument, it's a mouthful. Nessi is much better. Take for me. We actually have Nessi right here at Palomar, and we'll be observing. We just observed with it, let's see, last Thursday. We'll be observing again in about 2 weeks. And we're actually using it on the 200-inch Hale telescope. This was a telescope that was commissioned in 1948, 50 years before the first exoplanet was ever discovered. This is actually the world's largest telescope for over 50 years as well. And despite this instrument, this telescope being built 50 years before even the first exoplanet was ever discovered, the telescope's basically the same. The only difference is we have our instrument connected to it as well. So really, it's quite incredible what we're able to do just by swapping out an instrumentation for to discover and also characterize exoplanet atmospheres. So that's a cool picture of Palomar here with the 200-inch Hale telescope. So let me show you a picture of the instrument itself. Here's a picture of Nessi. No, I'm sorry, that's a mythical sea creature. Sorry, everyone. All right, here's an actual picture of Nessi, right here, the blue thing on its handling cart. Here's some of its hardware. There's a big tank of liquid nitrogen in the back. And I'm taking some images in one of the rooms at Palomar. Nessi is actually installed at what's called prime focus. So when you think of a telescope, you have the light come down, hits the primary mirror, it gets reflected up to your secondary mirror, where then the light goes down through your hole in the bottom of your primary, through your cast focus. And that's where your eyepieces typically are, or your cameras typically are. Nessi, however, is actually installed at the top of the telescope. It actually takes the place of the secondary mirror. So light comes in, hits the primary, is reflected back directly up to Nessi. The reason we do that is to actually preserve a very wide field of view so we can see as many targets simultaneously as possible. But to get Nessi up on top of this observatory, we have to do lift tests. So here's actually the principal investigator of Nessi. This is Michelle Creech-Ekman. She is a professor at New Mexico Tech. I love her shirt, which says, "I want to believe," and has a picture of Nessi on it. Here's my direct boss at JPL, Mark. He is ignoring me like usual and getting some cool photos. And you can see actually Nessi is being lifted up in the air right now. We're actually having to lift it off the observatory floor to put it where the secondary mirror is, about 100 feet up in the air. So we have to do a lift test to make sure it fits on the top of the telescope and nothing bad happens, right? So we're lifting it up in the air. It's going higher and higher. Right about now, I'm really hoping that our insurance started, because I don't want our instrument to fall on top of this very priceless 200-inch primary mirror that's very, very historically significant. And luckily, sort of spill the beans here, Nessi did get successfully installed at the top of Palomar. So here's actually Nessi installed at the prime focus cage. Here's my boss, Mark. We're doing some computer tests to make sure the computer's working properly. He's smiling, but actually he's laughing at me, because if you remember, I am the commissioning lead on Nessi, so I have the joy of going up 100 feet in the air to work on it. I'm also deathly afraid of heights, so he's actually laughing at me because I'm basically peeing my pants. But needless to say, Nessi is properly installed and got this cool photo, almost looks like a spacecraft. You actually see my shoes there as well. And we actually got some really amazing data with Nessi already. This is about within a factor of 2 of the precision of the Hubble Space Telescope. So we can continue to get very precise measurements with Nessi on the 5-meter or 200-inch Hale telescope down here in California, right between LA and San Diego. I'm seeing a question in the chat is water fairly common on exoplanets? And the answer is actually yes. Water is actually one of the most abundant, if not the most abundant molecule in the entire universe. So when Hubble is looking for planets or looking at exoplanet atmospheres, it actually has an instrument on board that is just happens to, or by design actually, probes water absorption. So that's about 1.1 to 1.7 microns, or right here. So this one instrument has the wavelength range that can probe and look for water content on the atmospheres of these planets. And what people are finding is that exoplanets typically all have water in their atmospheres because it is one of the most numerous molecules in the universe. But water in the form of gaseous water vapor, because a lot of these planets are still way too warm for water to survive on their surface. So this is actually a plot of about 30 planets. Right here is actually the telltale shape of water. And right down here is a very flat atmosphere. What this infers, though, is that that planet probably has water in its atmosphere, but there's a high level of clouds, a cloud deck, that gets in the way of us observing the water. So rather than seeing this really nice water absorption feature, we see a cloud, which spectroscopically looks like a flat line. And they've arranged the planets right here from cloudy all the way up through clear atmospheres. This is basically a spectrum of clear to cloudy atmospheres. So we're actually able to also observe weather on these exoplanets by looking at their clouds as well. See, another question I got in the chat was, is Nessi both at New Mexico and Palomar? So Nessi was built at New Mexico Tech, and it's now being explicitly used at Palomar Observatory with the 200-inch Hale telescope. So it's out here in SoCal, hopefully for a long time. Also see another question about in the chat of any off-the-shelf instrumentation that direct imaging and spectroscopic imaging of exoplanets, or is each design custom? And is there a small group of physicists and electronic engineers specializing in this? And the answer is yes. There's a whole sort of, not industry, but group of folks that work explicitly on direct imaging. And as far as I'm aware, for direct imaging, you need that chronograph hardware. And to get that hardware, it's all custom made for that telescope, for the wavelength of light that you look at, for the secondary spiders, that are holding your secondary mirror, for example, in place. The size of your telescope, the shape of your mirror, it's all custom designed for that explicit observatory. As far as I am aware, there's no sort of, buy one, get one free or one size fits all sort of instrumentation you can buy it at Walmart or Costco or anything. All right, so thanks for those questions. So Nessi is observing right now, and hopefully you'll be seeing some results from that soon as well. So that's how we observe exoplanets. We use methods like the radial velocity, the transit, the direct imaging methods to discover planets. Then we look at their spectra or their light and apply Beer's law to characterize their planets, to figure out what sort of molecules are in their atmospheres. And then allows us to take that next step to find life on the surfaces of these planets. But how do we find life? Well, let's make a thought experiment. Let's take a spacecraft. Let's launch out into space to study the outer reaches of the solar system. But as it's going to the outer reaches of the solar system, we have it turn around and turn on its instruments and look back at the Earth. What sort of signals would we expect to see in the Earth spectrum that would indicate that life exists on its surface? Maybe you can look for evidence of oxygen. For example, ozone is produced by plants and algae. But you can look for liquid water on its surface, or water in its clouds or its atmospheres using Beer's law. Or we can look for signs of biological activity like cow farts, right? Like methane. But we have to rule out all other explanations. Just because you see oxygen or water or methane in the planets of atmospheres, in the atmospheres of these planets, does not mean that life necessarily exists on the surface. These molecules can all form abiotically without life. We're seeing water in the planets, these atmospheres. We're seeing methane in the atmospheres of these planets. So you have to conclusively detect or rule out, really, all other explanations other than it being from life. And this is actually a big outstanding question in our field, are what sort of molecules, what sort of bumps and wiggles are we looking for? What sort of biosignatures are we looking for? That if we see their signature on our spectrograph, that tells us that that thing has been formed conclusively by life. And that's actually an outstanding question that many astronomers are actively researching right now, trying to figure out what those biosignatures are so that we can conclusively say that a planet has life on its surface. I got another question in the chat about Nessi again. And the question was, how much time do I have on the 200-inch? I think I roughly average about 10 nights a year. So about 4 to 6 nights, maybe 8 if I'm lucky, one semester, and another 4 to 8 in the other semester. So just a week or two over each year. Jerry's asking in the chat, could I detect artificial lighting on the night side of an exoplanet? So actually, some missions are looking into this. So SETI, I believe, just published a paper about looking for artificial lighting, much as we have on our own Earth on the night portions of the planet. And I think, I'm not really too sure though, but I believe they probably have done a study on this, whether the next generation missions that will launch after Roman have the capability to observe these signals. But these signals are very, very small and hard to see. So it requires very high precision, very precise instrumentation and large telescopes as well. Right, so that's how we find life is, and honestly, it's still an open question. What sort of combination of molecules do we need to see to conclusively say that this planet has life on its surface or not? Or we can just build spacecraft and send them out and talk to aliens firsthand. Voyager 1 and 2, also built at JPL, were launched in the mid-70s, and they did this grand tour of the solar system. But they also had these really cool golden records on board. And these golden records had recordings of people saying hello across the world, also sounds across the Earth, and pictures of the Earth as well. And here's how you actually set up your phonograph to look at the data. Here's the expected signal. Here's how you project the image on your TV screen. And here's where the signal came from relative to a bunch of pulsars in the galaxy. So it says, hey, here we are, here's what we look like and sound like, and here's where you can find us as well. Similarly, back in the 70s as well, Frank Drake and Carl Sagan wrote a message to aliens using Arecibo, which was the world's largest and then second largest telescope. This was a giant radio telescope so big that it fit in the valley between mountains of Puerto Rico. And they sent this message on the right out to this globular cluster M13. And they said, hey, thousands of stars here, probably thousands upon thousands of planets. And here's the message they sent to aliens that could be living there. We have, hey guys, here we are, we're humans. This is what we look like. At the top, this is actually talking about numbers and counting. Here is about molecules and atoms. Right here, that double helix structure, that's DNA. Here's a map of our own solar system. There's the sun, Mercury, Venus, Earth, elevated because we're from Earth. Mars, Jupiter, Saturn, Uranus, Neptune, and guys, this was the 70s. If they didn't know any better, they have Pluto on here. Ugh. We now know that Pluto is not a planet, so we'll forgive them. And this big purple thing down here is actually a side image of Arecibo. So it's saying, hey guys, we're humans. We know how to count. We know about molecules. We know about DNA. We think we're pretty smart. Here's where we live. Please don't invade us. So hopefully we'll just keep the cast from Independence Day alive forever to save us. More recently, though, people have sent messages to other exoplanets that we have actually discovered in the last few years. So for example, there's a social media campaign on by a network called Bibo. Here it's big in Europe. And they sent 501 messages to this solar system called Gliese 581. This is a red dwarf star. So just like that question earlier, it's a star that's much smaller than our own sun. And its habitable zone is much closer to its sun as well. Basically, you can sort of think of like a campfire, right? If you have a giant bonfire, you can stay warm and still stay very far away from that campfire. But if you have a small little campfire out in the middle of the desert, you have to get very close to the flame to stay warm. And I'm seeing a connected question to this is how well would photosynthesis work for a planet around a red dwarf star? I'm actually not too sure about the answer to that question, in all honesty. let's see, I'm assuming that the life that would exist on that planet would likely probably have to do photosynthesis and either do it less efficiently because the star is emitting less yellow light, or perhaps tune its wavelength to take advantage of that redder light from the star as well. So this is a social media campaign because nothing bad happens on the internet, of course. And this message was sent about 20 years ago, or in 2008. And the system is 20 light years away. So the message will arrive in early 2029, and a reply, if immediately sent back to us, will arrive back at Earth in 2049. So it really goes to show how difficult it is to do interstellar communication, given how far away everything is and how long it takes to communicate from one part of the universe to the next. All right, so where are we now? Well, unfortunately, and despite what the History Channel might tell you, we have yet to make any conclusive detection of extraterrestrial life. And the question is, why haven't we? We now know of over 5,000 exoplanets. Thanks to NASA's Kepler and TESS, we know that planets are as numerous as stars, if not more so. Planets are everywhere, they're ubiquitous. And if they are, why have we yet to find any extraterrestrial life? Well, maybe our technology isn't good enough. And I would argue this is definitely the case. It wasn't, that I argue myself, is it wasn't until we had digital cameras on the back of telescopes that enabled us to observe transiting exoplanets and discover them and to find them finally. Or maybe we just haven't found them yet. Maybe we've been looking at this part of the sky and they've been talking to us from this part of the sky. Jill Tarter, she's a SETI scientist. She's actually the inspiration for Carl Sagan's Contact, and the Jodie Foster character was modeled after her. She said that if we took the size of the universe and shrunk it down into the size of the Earth's oceans, despite everything we know and have explored, we only have really explored the equivalent of 1 cup of water's worth. So there's still a ton more out there to explore, discover, and understand. Or to leave you on a sad note, maybe you are all alone. Maybe life is really that infrequent, and maybe it only exists here on the Earth. Personally, I'm a bit more optimistic than that. I think life exists elsewhere out there. We just haven't had the technology or the technological means yet to discover it. But looking forward to the future, it's very, very bright for exoplanets. We have this amazing foundation provided to us by ground-based observatories that have used the transit, radial velocity, and direct imaging methods. We've been very lucky to use a variety of recent NASA missions, such as Hubble and Spitzer and Kepler and TESS, to look at and characterize and discover these exoplanets. James Webb, which will be observing his first exoplanet this month, literally within days. Really excited about seeing the data quality out of that. The Nancy Grace Roman Space Telescope, its coronagraph instrument, will take us the next step and enable us to look at true Jupiter analogs, Jupiter-sized planets in Jupiter-sized orbits around solar-like stars. That's taking that ground-based technology and applying it for the first time on a spacecraft. Then that lesson learned from all of this foundation, all these great and excellent missions that have been launched and are currently in space, we'll be applying them to the next generation of NASA missions. The next NASA flagship mission they'll be launching in the 2030s and 2040s. And these missions have literally been designed to look for extraterrestrial life due to their size, due to their technology, due to their sensitivity. So perhaps in the next 10 to 20 years, we can finally answer that age-old question, are we all alone in the universe? And with that, thank you so much. And I'm happy to take any questions that you might have.
Rob Zellem, can you hear me? Am I muted?
I can hear
I
you.
can hear you.
Okay, you had a spellbound there, Doctor. I got to tell you, I'm going to ask mine real quick. Is Proxima Centauri the first exoplanet ever discovered?
No.
That's not.
Yes, Proxima is not the first ever. It's one of the closest exoplanets to us, if not the closest. The first exoplanet ever discovered was 51 Peg B, and that was discovered in the early 90s. And Proxima Cen was discovered, I think, just a few years ago, like within the last 3 or 4 years. But it's the closest exoplanet to us, for sure.
And I'm imagining that among all the thousands of stars that are up there, a very small minority can be seen transiting on the edge because they could be in all kinds of configurations and would never know. Most of the stars, we don't know if they have planets because they don't transit, right?
Yeah.
Exactly, yeah. So we're just missing a ton of planets just simply because they're not in that correct geometry. So remember, for a transit, you need the planet to pass in front of the star along your line of sight and block out the star's light. But the planet can be in a bunch of other geometries as well and never transit its star. You would never know that it's there. Exactly.
All right, I'm going to throw it to the rest of the board. Mr. President, you got any questions?
Your one statement that we might be alone. My thought is we might be temporarily alone. Because in the Drake equation, technical civilizations have to have a certain span, and our span is only a few decades, as you point out, with cameras on the back of our telescopes. So we would have to hit another technology that's at least as far along as we are. And look at how many billions of years it took our life-supporting planet to get here. So
yeah. Exactly. But there also could be life around star systems that are millions of years older than our own Earth. So the sun, so the sun is relatively young, or it's kind of an average age star. There are other stars out there like red dwarfs that are millions of years older, and their planets could also be millions of years older as well. So maybe there is a technologically advanced civilization there as well.
So when our signal gets to Gliesa in 20 years, may get a statement back immediately that says your call is important to us, and then music starts playing.
Voicemail. Okay, Chuck and Pat, do you have anything you want to ask?
Well, I got the email early on when you were starting up this exoplanet watch, and I do asteroid occultation with IOTA, and there's a whole bunch of people that do that. And the formats, we tend to use, video, and a lot of that the newer cameras do fits, but a lot of people are using the older video cams that produce AVIs and other video type formats. So it wasn't really friendly for the kind of data that you needed.
Yeah, that's pretty cool. You can use the cameras. I wonder how good the image quality is. You might be able to actually contribute as well with your video cameras. Yeah, definitely reach out on our Slack channel. That's the easiest way to get in touch, or send us an email. We'll love to take a look at your data and see if there's a way we can maybe support that as well. But we're finding that you actually don't need very expensive cameras at all. We actually use like a $200 ZWO camera. That's it's a Bayer array digital color camera, and we threw this on the back of a 6-inch telescope with an equatorial mount. And then one of our interns actually was observing from Caltech campus, and the astronomy building is right next to a very bright athletic field. And despite all that, despite being in downtown Pasadena with this relatively inexpensive camera system, he was able to actually get observations last December that are now being published, that have been just recently submitted yesterday to a journal. So you really don't need really expensive or fancy equipment to actively participate in this project, for sure.
But there is a pool of people out there with these video cameras that would probably be willing to collect data.
Yeah, so please get in touch, and I'd love to take a look at the data and see if there's a way we can support that. That'd be awesome.
Okay.
Really?
Thanks.
Chrissy, are you still here?
Of course, I've been watching with bated breath. What a fantastic presentation.
Yeah.
You have a question, dear?
Oh gosh, I mean, it was. I'm all aflutter with all these fantastic opportunities for citizen science, and I'm just super jazzed about all these upcoming missions. Super jazzed. Like you, Dr. Zellem, I've been exoplanets were the thing that turned me on to astronomy. I remember the day I read that news article about Pegasi 51, and it just like blew my mind. And I thought, I'm gonna do this for the rest of my life. So I really appreciate your passion and your work, and I cannot wait to see what happens next.
Yeah, well, thank you so much for having me. I really appreciate it. And thanks for those kind
that
words
was,
as well.
It's an exciting topic, and it was an excellent talk. Good job.
Thank you.
Tom Totten, our webmaster. You did a great job, Tom. Will you have a question?
No, I just want to mention that we do have the exoplanet, the citizen science. Chuck put that on the events page. So there's information there on the exoplanet citizen science. And hope we'll keep that there for a while.
Okay.
I'll throw it up on the screen as well.
If I can say one more thing, we actually had a high school student for a science fair project do imaging of the exoplanet that I think you showed in one of your images, which is near the Dumbbell Nebula, near M27, one of those Henry Draper stars. And she just used a barn door mount, basically, and a DSLR, and she got data on a transit.
That's probably actually the one I was talking about, literally. Yeah. So it's right by the Dumbbell Nebula. This is actually some data that one of our other participants in our project did. So Doug Lalla is an amateur astronomer. He does astrophotography and got this really awesome photo of the dumbbell, but also nearby is this transiting exoplanet called HD 189733b. It's a hot Jupiter exoplanet, and you can sort of kill two birds with one stone. You can make awesome images and also get really scientifically impactful observations of hot Jupiter exoplanets as well.
Well, Dr. Zellem, I read about or heard about it, and I think we all know there's going to be some sort of you mentioned blocking out the starlight by covering it with some sort of a disk. Isn't there this giant sunflower looking thing that's going to be up in space miles from the observatory?
Yeah, so that's called star shade. It's basically like I'm showing here. Instead of having this little disk only internal to your instrument, you can also do a formation flying and have your space telescope and have this, looks like a giant space flower basically, and have that pass in front of the star and block out the star's light. And that enables you to get to higher contrast. So you can look for objects that are a lot dimmer. I believe Roman was or is supposed to be compatible with a star shade. So Roman is that mission that I'm working on here at JPL. I haven't heard the latest status of the star shade and whether or not it's going to be going for launch or not, though.
Okay.
I've got a question. So Rob, are you involved in like doing the mathematical equation calculations as part of these projects? Is that under your, so you do have that kind of background to be able to do that? Okay.
Sometimes I pretend to, yes. No, yeah. I math, science background for sure, physics, astronomy, and also like other weird things like classics and jazz piano and hockey and stuff.
Well,
it's nice to see people using Python, which is so cross-platform that you can really increase your number of people helping out.
Yeah, and our entire project, Exoplanet Watch, is using Python explicitly. I was trained in as a graduate student or an undergrad, C and C++, and then grad school, C, MATLAB, Fortran, IDL. I was forced to learn Python at JPL, and it's great. I love Python. It's free. There's a great community of folks that are really helpful. And odds are, if you run into an issue, you're not the first person in the world to run into that similar issue. So there's a lot of great helpful websites out there. And all of our coding, whether they're simulations that we do for Roman, for the science calibration plan, or if we're doing it for transit observations with Exoplanet Watch, it's all written in Python.
It's also, from a software engineering point of view, a much, I guess you'd call it safer language as far as the behaviors inside of it. Yeah,
it's really a great tool. I like it a lot.
I don't know if you know who John Cleese is. He used to live here and he used Python. Actually,
yeah.
Never mind. I had a dumb question, but I don't know. They're sometimes so dumb. Can I just throw it at you and keep it short? And you may or may not be able to answer it. At the beginning of your talk, Dr. Zellem, you showed a star with a planet next to it orbiting each other, and they tug on each other, and they each have a circular pattern. So far, so am I correct?
Mm-hmm.
All right. The sun or the star has a small circle, and concentrically, there's the outer circle that the planet's going around. Some reason, I can't figure out why, in physics, I know it's natural, the sun or the star is always on the opposite side of its circle from, there you go. Why is it always on the opposite side? Why wouldn't it be on the closer to the planet side of its own circle? Do you understand the question?
Because of the mass.
Yeah. It's, like you said, because of the mass. So basically, rather than the planet orbiting around the star, what's happening is that the planet and star are orbiting the center of mass of the system. So a way to sort of think about it is like a teeter-totter, right? So if you put like one person on one side of the teeter-totter, you can actually put a very small person to balance the teeter-totter if you move them far out, or you can take a very large person and move them very close in, and you can balance out the teeter-totter. And that's basically what's sort of happening here, is you're sort of balancing the masses between the star and the planet and their distance from each other. And as a result, they're sort of orbiting around this sort of fulcrum or pivot point here, which is the center of mass of the system. And I unfortunately just got your John Cleese joke. It took me that long to remember Monty Python, sorry.
But our own sun does this to a degree, right?
Yeah. So Jupiter causes the Earth, or sorry, Jupiter causes the sun to wobble. I forget exactly how by much. I think it's a few centimeters. It actually wobbles back and forth. So even though Jupiter is, 10 times smaller than the sun in terms of its radius, it still has a gravitational pull that we can measure on the sun itself.
Okay, and if you ever discover an exoplanet that you think has life on it because of everything in its atmosphere, you still won't know whether it's modern technological civilization or ancient microbes, right?
Potentially, and that's what people are actively studying right now and looking for these biosignatures. Personally, I think that when we discover life, it'll likely be in microbial form, because if we just look at the Earth, the majority of our life is in microbial rather than human form, for example. And that's probably, in my mind, the most likely form of life for us to discover. But perhaps, like someone asked earlier about looking for lights on the night side of a planet, or maybe you can look for effects of pollution in the planetary atmosphere. That can maybe give you some insights on the technological advancement of that civilization, whether it's microbes or something intelligent, or maybe we're lucky and like contact, we can pick up the radio waves from the civilizations as well.
Whoa.
I remember reading once that a civilization coming here and looking has a possibility of deciding that automobiles are the dominant form of life.
Yeah, it's a Hitchhiker's Guide to the Galaxy reference, right?
Yeah, thanks
Okay,
for all the fish.
There we go. I'm getting back up to speed now.
You did good, Dr. Rob. We hope to get you back again someday with some updates for us. And if you ever come to town again, check with me or call one of us or whatever. We'd love to see you, take you out to lunch.
Yeah, that'd be great. I'd love to hopefully give a talk out there in person again. And yeah, I'd love any
We'd love to do
excuse to get
that.
to Santa Barbara.
They still do tours, do they not, of JPL? Because we're still looking for a field trip.
So they just started those up again in June. And the way to get that, if Astronomical wants to do that, I think you can go on, just Google, I think JPL tours. It's on the website. You can probably get a group tour, maybe going for your club. That could be pretty cool.
Okay, you got it, sir. Any other questions before we go? Everybody, we loved it.
Yeah, no more questions from me.
All right. Budding new scientist, astronomer from UCLA, probably will be our next speaker on this big screen when we reassemble live. Her name is Claire Williams from UCLA. Dr. Rob, thank you very much. An incredible report. The rest of you,
Thank you.
we'll see you at one of our outreach or at our big board meeting.
Yeah.
Thank you and good night. And we loved it. Thank you very much, everybody. Tom,
Thanks again for having me, guys. Appreciate it.
All right. You got it.
Bye.
Bye.
Gotta do it.